In the last chapter, we learned about several different types of discrete random variables, and now we turn our attention to continuous random variables. Many of the formulas we learned about last chapter that involve the sigma or summation notation, we're going to see very similar formulas this chapter that involve integrals. The big difference here is that instead of x only being allowed to equal certain values, now x can literally equal any value on the number line. So as an example, someone could weigh 150 pounds or 151 pounds or any number in between. Sometimes we round weight off, but someone's weight in reality, if we had a scale accurate enough, is a really long decimal number. As a matter of fact, if we had a scale accurate enough, we would never be able to find somebody who weighed 150 pounds exactly. Another example of something that's continuous is when you're driving a car and the car goes from 60 to 61 to 65 miles an hour. It doesn't make those moves in jumps or in jerks. It doesn't suddenly change from going 60 miles an hour to going 61 miles an hour like it leaps forward. It's a gradual progression, and it hits every possible speed in between 60 and 61 miles an hour. Time is another example of something that's continuous. When the minute hand is moving continuously around the dial, at some point it's 5 o'clock straight up. But the amount of time that it's 5 o'clock straight up is actually 0 seconds. It's kind of like, it would be kind of like in the world of integrals, integrating a function from 2 to 2. If the starting point is 2 and the ending point is 2, then you're kind of like finding the area of a rectangle whose width is 0. And along those lines, in the discrete world, there's a difference between saying x is less than or equal to 2 and x is less than 2. But in the continuous world, since there's no probability of x equaling a particular value, it doesn't really matter if we include the equal sign or not in probability statements. So it does, however, make sense to figure out the probability of a range of values. And in order to do that, since the values are continuous, we can't sum them up. We have to integrate over all possible values. So we're basically finding the area under the PDF. So the difference here is in chapter 3, when we were talking about discrete random variables, the PDF gave you the probability of a certain value of x. In the continuous case, the PDF tells you the height of the probability curve, but you have to integrate that curve in order to figure out a probability. So you're going to hear a lot the term probability or the term area be used interchangeably. And just like in the discrete world, we had every probability in the probability table had to add up to 1. In the continuous world, the integral of all possible values of the PDF equals 1. In other words, the integral of the area under the entire probability density curve has to equal 1. And the density curve has to be positive because we can't have any negative probabilities. We also have a cumulative density function or a cumulative distribution function, which adds up all the probability up to a certain point. So we're going to call that one capital F of x, and that's the integral from negative infinity up to x of our PDF. So the CDF is the integral of the PDF up to point x. And like we saw in the last chapter, we can calculate probabilities by subtracting appropriate values of the CDF. So if you want to know the probability from A to B, the probability that x is between A and B, you can, like up here, integrate from A to B, But you can also, if you have a hold of the CDF, you can just do the CDF evaluated at B and subtract the CDF evaluated at A. And that's kind of like the second fundamental theorem of calculus, and that gives you the same answer as the integral. And there's also something similar to our complement rule. And percentiles get interesting. If we want to find the pth percentile, you got to find a value A such that the integral from negative infinity to A of your PDF is P. So that means you're solving for a limit of integration. Now, sometimes that can be kind of nasty, but if it's easy to find the antiderivative of this function, then usually we'll get something that we can solve for A. We'll see that in a problem coming up in a little bit. In the world of discrete random variables, we had this formula for the mean. We added up the products of all the values of x times their probabilities. So in the continuous world, that formula is exactly the same, except now this sum is an integral over all the values from negative infinity to positive infinity. And we see something similar with the formula for variance. Instead of summing all of these values, we are integrating over all of these values. I like this version of the formula better. Integrate x squared times the PDF from negative infinity to infinity, and then subtract the mean squared. We'll see that coming up on a problem shortly. So one very classic example of a continuous random variable is the exponential random variable. And the exponential random variable looks something like this. So the exponential random variable basically has this format, e to the negative x. We kind of need it to be e to the negative x so that the graph is approaching the x-axis, so we'll have a finite area, and this parameter that's in the exponent is also out in front as a coefficient, and that's a way that the area under the PDF ends up equaling 1. Since the function e to the x is fairly easy to integrate, it's kind of easy to find out the CDF. Remember, the CDF of x is just the integral from negative infinity to x of the PDF. So in this case, the integral from negative infinity to x of lambda e to the negative lambda t. By the way, some books have that parameter lambda as an a, and some have it as a b, and so on. Also note that our PDF is 0 for negative values of x. So in other words, our function only exists for positive values of x. So we're going to change that lower limit of integration to 0. And then the antiderivative of lambda e to the negative lambda t is negative e to the negative lambda t. Little verification over here. And we evaluate that at 0 and x, and we get 1 minus e to the negative lambda x. So if you don't want to have to integrate on the midterm, then just remember that this is the CDF, and the integration's already been done for us. You can also use integration to find the mean. Remember, we were talking about this formula up here for the mean involving integration. So we'll integrate x times the PDF. So x, lambda e to the negative lambda x. And again, we would normally do that from negative infinity to infinity, but our function only lives from 0 to infinity. So we'll do that integration. And this is going to involve integration by parts. And I won't bore you with the calculus details of the u dv and the v du and all that stuff. But anyways, if you integrate this using integration by parts, and you evaluate this from 0 to infinity, you get the antiderivative of that and evaluate it from 0 to infinity. That all just comes out to be 1 over lambda. So this parameter lambda, which is sometimes referred to as a scale parameter, that's just the reciprocal of the mean. Or you could say that the mean is the reciprocal of lambda. We can also find the variance in a similar way. We have this formula up here. Where did it go? We have this formula for the variance that involves integration. So we can integrate x squared times the PDF. And if we integrate x squared times the PDF, it also requires integration by parts, but you have to do integration by parts twice. Long story short, the variance will turn out to be 1 over lambda squared, which means the standard deviation is just 1 over lambda, which means the exponential distribution has an interesting feature that the mean is 1 over lambda and the standard deviation is 1 over lambda. So here's a little example using the exponential distribution with a parameter of 2. And here's several questions. What is the mean? What's the probability that the random variable is less than its mean? What's the probability that it's less than 2 standard deviations above the mean? And what's the 90th percentile for this random variable? So since lambda is 2, the mean is 1/2. No calculations required there. The mean is the reciprocal of lambda. For the second question, what is the probability that the random variable is less than its mean? Well, that's going to be 1 minus e to the negative 1, or 0.63. You can do that totally algebraically, and notice I didn't do any integration here because I already know what the CDF is. So the CDF up to the mean, which is 1/2, plug it in, and there you go. Now on the calculator, I have put in the function 2e to the negative 2x, and then I graphed it, and then I integrated, just to double check the area that I just got, I integrated from 0 to 0.5. Takes a second to shade, and we see the area is 0.632, same as what we got algebraically. For the third question, what's the probability that the random variable is less than 2 standard deviations above its mean? So first of all, 2 standard deviations is 2 times 1/2. 2 times 2 standard deviations above the mean is the mean plus 2 standard deviations. So this expression is 2 standard deviations above the mean, and we want to know what is the probability that x is less than that. So that's really just what's the probability that x is less than 1.5. Plug that in. Any old scientific calculator will tell us this value here, and that's something that we can also verify on the graphing calculator if we wanted to, but e to some power is not difficult to figure out, so that's no big deal. For the last question, we want to know what value represents the 90th percentile. So what value of x, or I'll say a particular value of x called a, what value of x, call it a, gives us the 90th percentile? In other words, what value on the x-axis would have 90% of this area below it? So this is not too hard to solve. Using natural log, we get the e term by itself, then take natural logs, and we solve, and we get that the value of x for the 90th percentile is 1.15. We can also confirm that using integration on the calculator, confirm that the integral from 0 to 1.15 is in fact 90%. Very key point I wanted to bring up, you can also use this to find the quartiles, because quartile 1 is the 25th percentile and quartile 3 is just the 75th percentile. So you can use this method to find the quartiles of the exponential distribution. One thing I wanted to point out about the graphing tool Desmos is this is pretty cool that Desmos will solve for that limit of integration for us. If we do an integral on Desmos from 0 to a, and we're doing 2e to the power negative 2x dx. And we want to know when is this equal to 0.9. And we change the equal sign to a tilde. Desmos will figure out the value of a, the value in that limit of integration that makes this true, and it's 1.15, which is the exact same answer that we got earlier algebraically.